This is the lesson 12 in Theory of Computation. We go on to the decidability chapter. In this lesson, we will talk about countable and uncountable languages. We must first begin by defining the term cardinality. Later we will talk about the cardinality of the set of numbers and countable sets. Simply, cardinality is a measure of the number of elements of a set. For example, the set A contains 4 elements A, B, AB, BA, and therefore the cardinality of the set A is 4. In other words, the size, or cardinality of A is 4. You may remember this term from your background in set theory. Mostly in mathematics, students use this term for a finite number of sets. But, what about those with infinite elements? For example, what is the cardinality of a language L made up of binary words? Any set X with cardinality less than that of the natural numbers is said to be a countable or finite set. Any set X that has the same cardinality as the set of the natural numbers is said to be a countable or countably infinite set. Notice that both finite and countably infinite are called countable here. Any set X with cardinality greater than that of the natural numbers is said to be uncountable. Therefore, we will focus on counting using natural numbers. The set of integers is countable. Here, with a little animation, we show how we label integers with the elements of the set of natural numbers, in other words, how we count. The number line of the set of natural numbers is used by stretching it as if it were made of rubber to count a set that appears to be twice as long as itself. Now you can imagine how we could use natural numbers to count other sets. The set of clean star is countable. Here our sigma contains only symbols A and B. Sigma star starts with epsilon and it contains strings A, B, AA, AB, BA, BB, etc. When we use natural numbers to count all the elements in a sigma star, a pyramid and a red spiral are made as follows. Here, red numbers are natural numbers. You see, counting the set of clean star is easy. The set of rational numbers is also countable. In this representation, we first need to remember that rational numbers are calculated by taking the ratio of two integers to each other. With this logic, in a two-dimensional table, the rows change the numerator value and the columns change the denominator value. After preparing such a table, natural numbers start counting rational numbers using Cantor's zigzag labeling method. The example on the right shows which rational number is marked by a few natural number labels. Both integers and rational numbers are countable with this logic. But what about the set of real numbers? Is it also a countable set? Could Cantor's zigzag labeling method be used here as well? Considering that the real numbers are indeed an incredibly large set, we can say that this will not be enough. Okay, but have you heard of Cantor's diagonal argument? Here we will see Cantor's diagonal argument about real numbers. Considering that the real numbers are very large, it was thought that it would be very difficult to discard the integer part and label only the real numbers between 0 and 1. Therefore, after the point, infinite numbers that are assumed to be of infinite length are written one down the other. In the example here, the numbers are specifically mixed up. After all, we can say that this is not a concern as we have to write infinite numbers. After this process, each digit on the diagonal in the list is marked in red. Like the first digit after the dot in the first line, the second digit after the dot in the second line. Selected red digits are written at the bottom and it is evaluated whether there is a new number. Do you think it could be a new number? You can say no. The red number is probably somewhere in the list. And now it's magic time. We will try a method to write a new number. Each digit on the diagonal marked in red is changed and written at the bottom. If the first digit is 2, then we have to write a digit other than the number 2. Here we started with 7. Red 9 appears in the second digit. So we have to find a different number. In the figure, 4 is written instead. So we try to write a new number. The number has been written, but we need to explain with a logical explanation that the new number is really new. The bottom number is different from the first row because its first digit is changed, and it is also different from the second row because its second digit is changed. This explanation goes on like this to an infinite number of numbers. Therefore, it is considered that a new number has been added, and we say that it is not possible to count real numbers with natural numbers. If Cantor's diagonal argument is applied on the set of all languages over a Knight alphabet such as binary symbols, we can first think of the symbols 0 and 1, then A and B in the same way. The lists we have prepared here represent a set of infinitely long binary strings and, in fact, all possible languages. Again we make the diagonal red, try to add a new string below. But we say that it is not possible to count the set of all languages, since it is possible to add a new string here, as in real numbers. Now we will talk about the relationship between countable and enumerable languages. If P is an enumerable problem or language, then the P is also countable. But not vice versa. Because we know that sigma star is countable, so all its subsets are countable. If every countable language were enumerable, then every language would be decidable. That's all. Thanks for listening.